Welcome folks, and in today's lesson we're going to talk about the topic of resonance as it relates to acoustics and sound and other things. And I'm going to start with a bit of a wordy definition here, and then we'll move on to talking about different phenomena and looking at some practiced examples. So resonance is a phenomenon of increased amplitude, this here is important, that occurs when the frequency of a periodically applied force is equal to natural frequency of the system. So there's a lot in that. We're just going to break that down. So when we talk about resonance, I'm going to use this as an example. This person on a swing, stick person on a swing. Now you know from hopefully pushing swings and seeing swings before that if a person is on a swing and then a person applies a force and pushes, then of course that swing is going to travel down and back up. And the best time to push that person on the swing is to push them exactly when they're at their high point and to match that frequency of that cycle of the swing. And if you can match that frequency with an applied force of the same frequency, then you will increase the amplitude of that swing. In other words, this person will go higher and higher. The person on the swing will go higher and higher. Okay, so that is what resonance is. There are many different applications of that principle of resonance. When you listen to the radio, that's resonance at play because you're tuning into a frequency which your receiver is matching the transmitter's frequency. There's also resonant frequencies when we talk about circuitry. It also comes into play in terms of engineering. When people are engineering bridges, architects have to think about resonance because if a frequency of a natural system or material is matched, then its amplitude, it can start shaking quite wildly. So another example is in acoustics in the musical world. An example would be an Australian instrument called the didgeridoo that Aboriginal folk in Australia like using. And I'm just going to look at this in the context of the musical instrument in a closed, from now on, I'll discuss this as it relates to closed air columns and what that might be. So just a little bit of background here. When you have a pulse, a wave or a pulse, which is moving and hits a fixed end, in other words, it can't move, then this pulse is going to be reflected in what's called out of phase. So on the way back, the reflected pulse will be out of phase, will be, opposite, if you like, than the incident pulse. And at a certain point, at the fixed point here, it is not free to move, and this is something that is called a node. Now, if it were free to move, it would just bounce back. It would not invert. It would bounce back as it approached the incidence, and the reflected pulse would have the same pattern. So why is this important? Well, we can bring our learning of the didgeridoo and our knowledge of this when we look at these harmonics and as it relates to musical instruments. So what are we talking about here? Well, when a wave enters an open column, it is free to vibrate. It creates an antinode. When those air molecules reach a fixed end, it's not free to vibrate, and therefore it creates what we call a node. So let's look at what that looks like in terms of a closed air column. In a previous video on my playlist, I've gone through the patterns for an open air column, a column that would be open on both ends. But in my example here, I'm going to look at one where it is open on one side and it is closed on the other side. So just like a didgeridoo, also a clarinet would be another example. So I've put a standing wave pattern at the very top here that we can use as a reference point. The red is for the incident wave and the green is the reflected wave. So when a sound enters a closed end tube, at the entry point it is open and the air molecules are free to vibrate. And so what's actually going to happen is it is going to give us a antinode pattern. So it's free to vibrate at its maximum at that point. But when it reaches the end, the closed side of the container, you will get a node. In other words, that reflected bounce wave, right at that point, it's not free to move. So this is the incident wave, this is the reflected wave. Normally you draw both when you're drawing these harmonics. And basically when the sound enters this point, the lowest frequency you get is when you can fit the highest wavelength, biggest wavelength pattern, where you've got an antinode on this side and a node on this side. So if we go to our example above, then that would be when we have an antinode here and a node here. Now that, hopefully you can see that that's actually a quarter of a wavelength. So that length here is a quarter of a wavelength. It represents a quarter of a wavelength. And for a closed column, this is what the first harmonic is. So in other words, a quarter of a wavelength is equal to the length of the tube. So if we keep the length of that tube fixed, we can hit other harmonics. And what that means is other frequencies where the natural frequency of that tube is going to be matched, and we will get an increased sound or amplitude. So the next harmonic that we can hit is when, and we're going to put it in a different color so we can see it here. Let's choose a different color. Let's choose this one. So when we go from a anti-node and we go past the node, because that's the first harmonic, and we continue and we hit the next time we hit the node, this is represented in our second example here. And this is actually three quarters of a wavelength. That's shown. If you look at the red line, it represents 3/4 of a wavelength. And because of that, it is the third harmonic. Now in a closed end column, there is no second harmonic. And the pattern continues here. We would have 5/4 of a wavelength is equal to L. And what that would look like, we're just going to do that right here. We're going to start over here this time, and we're going to go hit the first node, then the third harmonic, and then the fifth. So you would get that sort of pattern. If we look at what that would look like in a red, it would go down, then it would go up, and then it would go back like this. And the reflected pattern of this is going to be the opposite. And let's just mark in where we have our nodes, okay? So our antinodes are where it's free to vibrate. So in the third harmonic, there's actually another node here. There's an antinode here and here. And in the fifth harmonic, we have antinodes here and here. We have a node. We have a node, and this, of course, we said is the fifth harmonic. Okay, so hopefully that from that you can actually see that we have a little bit of a pattern here, and you can write, basically you have a situation where the length of that column is proportional to the wavelength. And for a closed end situation, closed on one, open on the other, a column closed on one, open on the other, the length is equal to 2n minus 1 times lambda over 4, where n can be 1, 2, 3, 4, and that gives us a pattern which we're going to look at. So the pattern, the summary table for the pattern is based on screen here. You can see for the first harmonic, there's one node, one antinode. The inversion of that equation is a lambda is equal to 4 times L. And then it goes from there, and you'll see that there's patterns. So the 7th harmonic would be the next one that we didn't talk about. There's 4 nodes, there's 4 antinodes, and lambda is 4/7 L. So just to look at an example here, a tuning fork with a frequency 256 Hz is held above a closed air column while the column is slowly increased in length. And how would you get that increased length? Well, you could have a scenario like is shown on screen here. So we've got that fixed tuning fork that's going to vibrate 256 times a second. And you could move this column up or down in water, and basically it would give you this area here. That is the column, the air column. So it's closed because of the water and open at the top. This is a very common lab that's sometimes done to get the speed of sound. What lengths for the column would the first four resonant points be found if the speed of sound was 340 meters per second? Of course, you may not be given that. You might just be given a temperature and asked to solve for the speed of sound. But we're just going to use a basic wave equation here. V is equal to F lambda. And we're going to put in our values here. And we're going to have 340 meters per second over 256 hertz. Of course, hertz is per second. And that's going to give me about 1.33 meters. Okay, so this is, if you like, the wavelength, and that's the wavelength for that particular tuning fork. And as you change the lengths, because now the frequency is fixed, you're going to get these harmonics at different lengths. So for each value, we would put in what the wavelength is, and we would get different lengths created each time. Okay, and we follow the equations that are given. And of course here we're going to see that this is 0.3325 meters, and the next one up as an example would be 0.9975 meters. And what that means is as you increase the column, the lengths, you'll start to notice a higher amplitude for that particular sound at those particular lengths. And this is what certain musical instruments are based on, this very concept. I'm just going to leave you with a practice question here, talking about DIY musical instruments. We've got one here called a tubulum, which is just using maybe PVC pipes of different lengths to produce different resonant natural frequencies or harmonics. So a tubulum player uses a column of length 17.2 centimeters. Let's just say this one right here. The speed of sound in the tubulum is 340 meters per second. Find the frequency of the first harmonic. So the first harmonic is something which we sometimes call the fundamental frequency. And so if I'll just write that in here, the first harmonic is called the fundamental frequency, and all subsequent harmonics above that are known as overtones. So you know, the second harmonic might be called the first overtone, and so on. It would continue getting. So that's one on screen that you can maybe use as a little bit of practice for closed end columns. Hopefully this video has been useful in terms of an introduction to a concept which covers many different areas of society, and hopefully the practice question helped you to see that in terms of mathematics. If you like this video, don't forget to give us a wee thumbs up and hit that subscribe button, please.